The motion review. It's all in the abstract, so there's no numbers. And probably the biggest thing that you want to remind yourself is that if an object is moving in a circle, it is being forced to move in a circle. Objects move in straight lines unless acted on by some other force. Now, if there's a tangential force, then they could be speeding up or slowing down, moving in a line. But if there is an inward force, what they would call a centripetal force, then the acceleration is inward and the velocity is there. And so the velocity would be tangent, but the acceleration caused by some sort of inward force then bends you into a circle. So the classic example is just a car turning on a road, right? The only way we are able to turn while driving a car is the fact that there is a force, namely the force of friction, that allows us to then move in a circle. And so we start out with F equals ma, the force is mu mg, and then we replace a, which is centripetal acceleration, by v squared over r. And if we wanted to, then we could solve for an equation for the maximum velocity we can turn with. It's based on how good your tires are, mu, and the road conditions, what planet you're on, g, and then how tight you want to turn. You can go faster if your tires are better, your planet's got a bigger gravity, and if you make a wider turn. Again, this is the fastest you can go without slipping. And you go any faster than that, friction's not going to be big enough to turn you. And again, there must exist some force turning you if you are moving in a circle. Okay, here's the classic cosine ride, right? This thing is spinning around and you are stuck to the wall. The force that's pushing you inward is the normal force. So in the radial direction, in the r hat direction, we have the normal force, which pushes you inward. And in this case, instead of replacing a by v squared over r, let's replace a by omega squared r. And vertically, well, gravity wants to pull you down. Friction of you and the wall is keeping you up. So as long as these two forces are balanced, then you won't move up or down. And you have the normal force of the wall, which is actually pushing you inward, which makes you move in a circle. And so what I did here is just set these two things equal to 0. And we also always know that the normal force, the force of friction is mu times the normal force. So I replaced the force of friction by mu n. N is m omega squared r, so I put that there. And then I just solve for omega. This value for omega would be the minimum amount you'd have to spin this thing. Again, this is in radians per second. If you wanted it in frequency, then you could divide by 2 pi to turn it into revolutions per second. And then you could change it into period if you wanted to look at the reciprocal of frequency. All those things are related. So if you were interested in a period, frequency, omega, velocity, all those things are fine. Once you find omega, then you can find all the other values. Again, this would be the minimum speed, angular speed, you'd have to rotate to keep the person stuck on the wall. All right, now we're going into more of a two-dimensional. This is our tetherball going around that plane at a constant speed. And the free body diagram, tension's up and right, mg's down. And so then we have a vertical component similar to the one above, where vertically t cosine theta and mg have to balance. And then we do have some sort of force making us move in a circle. And that would be t sine theta. This component, the horizontal component of the tension, is moving us in this picture to the right, which is inward. So it's that force causing circular motion. And the other thing I would add to the tetherball is that r is the radius of the circular motion. That's this horizontal distance here. That would be L sine theta. So the length of the string, sine theta, is then the actual radius of the circular motion of this plane. And then depending on what they gave you or what they wanted, you could take this and algebraically solve for whatever. So these are similar. There's a vertical piece that's balanced, and there's a horizontal piece that happens to be radially inward, and that's the force causing the circular motion. Here, I didn't actually write vertically, but of course, vertically down is mg and up is the normal force. Those things are balanced, and they don't really do anything, so I didn't write it. All right, the next we got our roller coaster. Roller coaster, ball on a spring, water in a bucket. You're spinning it up and down. You don't want the water to tip out. The fighter pilot, talking about the normal force he gets exerted when he's pulling G's. And so typically we look at the top, the bottom, and then like the side. If we want to look at the top, at the top here, the normal force and mg are helping each other. They're both down, which really means they're both inward. So both of those forces are helping you move in a circle. At the bottom, the normal force is up, mg is down, and in this case, gravity is hurting the process. The radial direction is upward, and so the normal force is trying to make you move in a circle. Gravity is opposing that, so they actually are opposite in sign, and the normal force is bigger at the bottom. Just look, if you solve for the normal force up here, it'd be mv squared over r minus mg, and here the normal force would be mv squared over r plus mg, right? We feel heavier at the bottom of the loop-de-loop because the normal force, the roller coaster, the plane, the tension in the string, all has to be bigger at the bottom because it's got to fight against gravity to make you move in a circle. Where up top, it's fine. Okay, other thing up top, what I didn't write on this sheet, square root of gr. Square root of gr is the minimum velocity you'd have to go to make it around the loop-de-loop. And think about what that means. The minimum velocity would happen if you let the normal force go away, and then you just have mg equals mv squared over r. The masses cancel, move over the r, take a square root. Again, the velocity, well, we can go as fast as we want, but if we go fast around the top, we need the normal force to help us. If we're going the minimum, the slowest we can go and still make it around the loop-de-loop, then we will let the normal force tend to go to zero, which then gives us the square root of gr, which is certainly something we've discussed and hopefully you have memorized. If you looked at the right side, well, then we actually have a combination. We're kind of back to the tetherball. We have one force that's vertically down, and in that case, it would cause a tangential acceleration, which means a slowing down. Think about it. When you're moving up the loop, you're slowing down. This is not uniform circular motion. Gravity is slowing you down, and exactly at g when you're on the right side here. Now, inward, well, the only inward force when you're perfectly on the right side is the normal force. So we have the normal force causing circular motion, and we have mg causing a tangential acceleration, which is slowing you down. Now, if you wanted the vector sum of those things, like the total acceleration, you'd have to take the centripetal acceleration, which would be that direction. You'd have to take the tangential acceleration, would be that direction, and you'd have to actually do the Pythagorean theorem, right? The total acceleration would be the square root of this guy squared plus this guy squared. Horizontal tabletop, that's about as easy as it gets. You just have a ball or a block on a string, and you're on a frictionless tabletop, and you're just whipping this thing around, and it's staying on the tabletop, so it's staying in that plane. Tension is inward. It's the thing causing circular motion, and circular motion is mv squared over r, where r is just the length of this string, right? The radius and the length of the string are the same thing. All right, pendulum. This is probably our classic example of a non-uniform circular motion, right? The object is speeding up as it falls down and then slowing down as it goes up. And so if you think about, and at this moment right there, what's happening? Well, as it's falling down, tension is inward, gravity is straight down, but really what we need is gravity opposing the tension out, and then gravity down the ramp. And if you think about, it is the exact same thing as something going down the ramp, like a box going down the ramp. The tangential direction is mg sine theta, and that's causing ma. So g sine theta is the tangential acceleration. That's the acceleration actually speeding you up. This up here is the circular motion piece. That's tension fighting against mg cosine theta, kind of like it was on a ramp. And that difference is what's causing circular motion, meaning mv squared over r. So again, this is an example where you have a centripetal acceleration, you're moving in a circle, and a tangential acceleration, because you're actually moving faster and faster and faster. And as you swung up the other way, well, then the tangential acceleration would be negative because you're slowing down. The banked curve, there's a whole video on the banked curve. I go through the equations. The whole bank exists because now that the normal force is pointed up and left, it actually points up and inward. Part of the normal force now points inward, which helps you move in a circle. And so I break down the vectors here. Think about these angles. This angle, and this angle are all theta. This part of the normal force, this part of the frictional force point inward, which cause circular motion. That part of the normal force points up, friction's down the ramp, down, and gravity's down, right? In this diagram, r hat is inward. That's our coordinate system. R hat is inward, and y hat is just up and down. Up and down are balanced, and there does exist some inward force causing circular motion. So I look at the bottom equation and I solve for the normal force. I then take that value and I substitute it into the top equation, do some algebra, and I get the equation for maximum velocity. We usually are interested in maximum velocity. How fast can we go around this curve? And again, the whole reason this exists is the bank allows for the normal force to help friction make the car go in a circle. You'll notice that if you let theta equal 0, so if you plug in a theta value of 0, that goes to 0, that goes to 0, so those go away, and you're just left with mu cosine theta over cosine theta, which is just mu, and you get mu mg, you get mu gr for the maximum speed, and that's exactly what we got up here when we didn't have any bank, right? The car turning with a non-bank is just mu gr, and then if we have our banked curve and we look at the limit as theta goes to 0, we actually get the exact same thing. So it makes sense that this equation works. All right, now we didn't do this during circular motion, but it is just circular motion. We're looking at satellites, moons, etc., orbiting in a circle. Again, Earth, here's the moon, here's a satellite. It's moving in a circle, F equals ma. This is the force of gravity, which is causing circular motion. There's mv squared over r. And if we solve that, we can quickly get the orbital speed of a planet in circular motion. If I wanted to derive Kepler's third law, then I could think about, well, here's the time. Time equals distance over speed. That's like back to 5th grade, right? Take this distance, divide it by the speed at which you're traveling, and that's going to give you the time. So if you take this and you kind of follow this algebra from here to here, you're going to get Kepler's third law, which says that the period squared is proportional to r cubed. So that's all circular motion stuff. And then I did throw one in there, elliptical orbits. That's not about forces. That's all about there exists no torque, and it's conservation of angular momentum. And you can do this guy, mv1r1 equals m2r2, and we can show that as r goes up, v goes down. Or you can look at I and omega and figure out what happens when r increases, what happens to omega. Now remember, this is an r squared in here. So doubling this would make that, doubling r would make that go down by a factor of 4. Where up here, doubling r makes v go down by a factor of 2, right? It's that ratio. Just be careful. Just depends on what the question's asking for. If they're asking for the velocity of the thing, or they're asking for the angular velocity of the thing. But elliptical orbits, not circular, not F equals ma, all about conservation of angular momentum. Every other circular motion, doesn't matter whether it's satellites, banked curves, tether balls, pendulums, vertical stuff, horizontal stuff, COSI, cars, it's all F equals ma. Decide what forces are causing circular motion. Replace A either by v squared over r or omega squared r. I'd say the COSI ride is the typical one where they're interested in omega frequency or the period, because you want to figure out how fast something is going to spin, where the car turning is about how fast the car could drive. Maybe another one like the COSI one is take like a turntable, right, which is just a disc, and then put like a coin on it, and then spin that turntable and figure out when the coin's going to slide off. Again, that might be something where you're looking at omega and frequency and not velocity. But certainly F equals ma, replacing A by v squared over r, and then rocking and rolling, and knowing that there must exist an inward force if you're moving in a circle. Now, there might be other forces, but if you're moving in a circle, there's an inward force causing you to move in a circle.